Good morning, everyone. This is our last official lesson for the probability unit. I know that this online learning process has seemed so long, but I can't believe it. We finished perms and comms. We did finish the test, and this is our last lesson. The next video after this that you watch will be your colored sheet, and we're looking for our test around June the 2nd. So we're getting there, and then 1 unit to go. So, I want to congratulate all of you on that. The last lesson for probability is what we call a stochastic process. And it's actually pretty cool. I think it is anyways. Let's take a look at the theory and then we'll get into some examples. A stochastic process are a series of events where the outcome isn't known and isn't simply based on probability. The opposite of stochastic is what we call deterministic, where you actually know the outcome. Okay, so let's kind of put some common sense to these two definitions. For example, say that you get a quiz and you leave it completely blank. Handing it in completely blank is deterministic. You know the outcome. You know you're going to take a 0. If you guess on every single one of the questions, your mark now is going to be a stochastic process because there are several possible outcomes. You might still get 0. You could completely luck out and get 10, or you could get a mark anywhere between 0 and 10. So the difference between deterministic and stochastic is that deterministic, you know the outcome. Stochastic, you don't know the outcome. Pretty much everything that we've done in the probability unit is considered a stochastic process where the outcome is likely. Or equally likely. That's what we've been doing. We've been doing a lot of things where the outcomes are equally likely. I just haven't mentioned the word stochastic. Okay? Let's keep going. To solve today's problems, we're going to use a tree diagram, just like we did earlier in the course. So you're familiar with tree diagrams, coin tosses, etc. The only difference is that we won't consider each outcome equally likely. We'll assign specific probabilities to each step, which may or may be dependent on the previous outcomes. This is kind of the cool part that I think, okay? I'm sure right now you're thinking, I don't know if this makes a lot of sense. So let's step back for a second, and I want us to step back to an example that we did in the calculating probability lesson. Okay, so that's basically lesson 3. It says, what is the probability of getting 2 heads if you flip 3 coins? So hold on, let me just go through this with you. Well, coin number 1 has a true or false, or heads or tails, sorry. Coin number 2 has a heads or tails, heads or tails. Coin number 3 has a heads or tails, a heads or tails. And we're quite familiar that when we do a tree diagram, that we always write the outcomes. So tails, 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 heads, tails, heads, tails, tails, heads, 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 tails, tails, heads, tails, heads, 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 tails, heads, heads, heads. So we're attacking this exactly the same way that we did during the calculating probability lesson. And if we were looking for the probability of 2 heads, bottom number would be your NS, your total number of outcomes, 1, 2, 3, 4, 5, 6, 7, 8. Top number would be the outcomes with 2 heads, our desired outcome. So 3 out of 8, 0.375, 37.5%. Basic, easy question. We'd love it if we got it on a test because it would be very standard, no problem. Okay, now, how would we attack this from a stochastic perspective? So let me just scoot for a second to the left and let me draw on just another branch for a second. When I flip coin number 1, the chance of getting heads or tails is equally likely, 50-50. When I flip coin number 2, independent events tells me that the chance of flipping a head or a tail is equally likely, 50-50. Again, when I flip coin number 3, independent events tells me again that it's a 50-50 chance of getting a head or a tail. Okay, so fine. Now I had 3 branches that produced 2 heads. I had this branch right here, and I'm going to call that particular branch tails, heads, heads. And that's 0.5 times 0.5 times 0.5. I also had this branch right here, and I'm going to call that branch heads, tails, heads, 0.5 times 0.5 times 0.5. And finally, I had this particular branch right here, and I'll call that one heads, heads, tails, 0.5, 0.5 times 0.5. Okay, let's get the calculator out. 0.5 times 0.5 times 0.5 is 0.125, 0.125, 0.125. And what do you think is going to happen here? 0.125 plus 0.125 plus 0.125. Bingo bongo. Traditional way, stochastic way. Now, your question would be, well, Miss Martel, what do you think? Like, what should I use? When the probability is 50-50, I would probably go my traditional way. It's visual, you can see it, you don't make your chances of making a silly are less likely. But let me show you when your hand is forced to go stochastic way. Okay, I just wanted to prove to you that stochastic will give you an appropriate answer that we're familiar with, okay, with a question that we're familiar with. All right, let's flip when you're ready. Oscar is a nervous test writer. He figures that if he gets a question right on a test, that he has an 80% chance of getting the next question right. And if he gets a question wrong on the test, he has only a 40% chance of getting the next one right. He's writing a test with 3 questions. If he has a 70% chance of getting the first question correct, what is the probability? So right away, when I look at this, what am I noticing? 3 questions, just like 3 coin tosses. The only difference is, in a coin toss question, there is never a mention of any sort of probability. Why? Because it's 50-50 all the time. Very, very different here. He's got the same idea as the 3 coins with the 3 questions. And he can get the questions right or wrong very much like the coin toss of heads or tails, just different letters. So let me draw my tree. The difference between this question and the coin toss is that your probability at each of these stages is completely different. So hold on for a second. Let's get the tree diagram written and let's write the outcomes. Right, right, right. Right, right, wrong. Right, wrong, right. Right, wrong, wrong. Wrong, right, right. Wrong, right, wrong. Wrong, wrong, right. Wrong, wrong, wrong. So again, super, super similar to the tree diagram, just different letters. Now, let's go back to the wording of the question. The wording of the question tells me that he's got a 70% chance of getting that first question right. That being said, if he's got a 70% chance of getting it right, he's got a 30% chance of getting it wrong. Okay, let's go back. If he gets a question right, he's got an 80% chance of getting the next one right, 20% that it's wrong. Notice, adds to 1, adds to 1. Let's keep going. If he gets a question right, he's got an 80% chance of getting the next question right, meaning 20% wrong. Now, hold on, stay with me. Okay, what if he happens to get a question wrong? He only has a 40% chance of getting the next one right, which means that he's got a 60% chance of getting it wrong. This is where stochastic can cause little sillies because there's a lot of little branches, a lot of little numbers. It's a detailed type of question. If he gets it wrong, 40% chance of getting it right, 60. If he gets it wrong, 40% chance and 60. Now careful, careful, careful. If he gets it right, 80% and 20%. So again, the only thing that looks different about this question are all the little red numbers. It's a classic tree diagram. It's just the probability is not a 50-50 at each stage. Okay, so hold on. Let's take a look at our part A and our part B. What's the probability that he gets perfect on the test? Well, perfect is the right, right, right option. 0.8, 0.8, 0.8, 44.8%. Excellent. What's the probability that he passes? And they're considering, I'm going to get a different color here, they're considering at least 2 out of 3. So that means 2 rights and a wrong, or all 3 rights. Okay, so hold on, I'm looking for 2 rights. Here's one. I'm looking for 2 rights. Here's one. I'm looking for 2 rights. Here's one. And I'm looking for 3 rights. At least 2. So 2, 2, 2, and 3. Okay, so I've got a little bit of work ahead of me. And again, this is where I got to be careful. So I'm going to have right, 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 plus right, right, wrong, plus right, wrong, right, plus wrong, right, right. Okay, so 0.8 times 0.8 times 0.8. Oh, uh-oh. Has anybody caught me? This should be 0.7 right here. Just recognized it. Nobody caught me. You would have if we would have been in class. 0.7 times 0.8 times 0.8. Sorry about that. Now we've got right, right, wrong. 0.7 times 0.8 times 0.2. Now we've got right, wrong, right. So hold on, let's go over that one more time. Right, right, right. 0.7 times 0.8 times 0.8. Right, right, wrong. 0.7 times 0.8 times 0.2. Right, wrong, right. 0.7 times 0.2 times 0.4. And wrong, right, right. 0.3 times 0.4 times 0.8. Again, you can just see exactly me making the boo-boos, guys. You can see it right there. So let's get the calculator out. 0.7 times 0.8. 0.448. 0.7 times 0.8 times 0.2. 0.112. 0.7 times 0.2 times 0.4. 0.056. 0.3 times 0.4 times 0.8. Let's add them up. 0.448 plus 0.112 plus 0.056 plus 0.096, 0.712. There's a 71.2% chance that Oscar gets at least 2 of the 3. That he either gets 2 of the 3 or 3 of the 3. I apologize, guys. Make sure you change that on your note. And again, like I said, this is very, very easily where the boo-boos can happen and where you got to be careful with stochastic. Kind of cool, though. Very cool. I like them. Okay, let's take a look at the next question. Lisa and Brad play rock, paper, scissors. Lisa knows Brad's pattern, so she wins 70% of the time. If they play 3 times, what is the probability that she wins at least 2 of the rounds? That's kind of very similar to this part B. Okay, so I don't even worry about anything until I get the question started. So there's round 1, there's round 2, and there's round 3. I'm going to call my letters, I'm going to use the letters L for Lisa winning and B for Brad winning. So again, the letters are the same in the sense of when we make our tree diagram, heads and tails, heads and tails, heads and tails. The only difference is we're Lisa's and Brad's, L's and B's, L's and B's. Always write down my outcomes. So Lisa, 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 Brad, Lisa, Brad, Lisa, Lisa, Brad, 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 Lisa, Lisa, Brad, Lisa, Brad, 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 Lisa, Brad, Brad, Brad. Again, the setup is identical. It's at this next part that we kind of go into stochastic mode. And we go into stochastic mode because the probability of Lisa or Brad is not equally likely. The probability is that 70% Lisa wins, meaning 30% Brad. Now, this example is a little bit easier because it's a 70-30 always. our previous example was more challenging because it had that if he gets it right, then there's a certain probability. If he gets it wrong, that idea. So actually, example 3 is easier than example 2. Okay. Now, picture's done, probabilities are done, outcomes are done. We're ready to actually answer the question. It says, what is the probability that she wins at least 2? So at least 2 means the probability of 2 and the probability of 3. Now, I want to show you something a little bit different because I'm hoping that in your brain says, geez, I could, with the word at least, use indirect, or we call it reverse psych. 1 minus the probability of 0 Lisas minus the probability of 1 Lisa. And we could have used reverse psych up here, but I just wanted to show you both, okay? So hold on. Let's highlight then 0 Lisas. There's 0 Lisa. And let's highlight 1 Lisa. Still going to be the same amount of work, even if we did it the direct way or the indirect versus reverse psych. It's still going to be the same amount of work in this particular question. Okay, so I'm going to have 1 minus Lisa, Brad, Brad, minus Brad, Lisa, Brad, minus Brad, Brad, Lisa, minus Brad, Brad, Brad. Okay. Well, Lisa, Brad, Brad, 0.7 times 0.3 times 0.3. Brad, Lisa, Brad, 0.3 times 0.7 times 0.3. Brad, Brad, Lisa, 0.3 times 0.3 times 0.7. And Brad, 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 0.3 times 0.3 times 0.3. Sorry about the spacing, guys. I actually might have to get another little paper underneath here. Sorry about that. Let's get the calc out. So 0.7 times 0.3 times 0.3 is 1 minus 0.063. I've got another 0.063, another 0.063, and now the last one is just that 0.3 times 0.3 times 0.3, 0.027. Okay, so let's make sure we're okay on that. 0.7 times 0.3 times 0.3 is 0.063, or 0.063. 0.3 times 0.7 times 0.3, 0.063. 0.3 times 0.3 times 0.7, 0.063. 0.3 times 0.3 times 0.3, 0.027. So hold on. .784. 78.4% chance that she is going to win at least 2 out of the 3. So again, with the word at least, you can either choose the direct method, like we did in example 2, or you can choose indirect reverse psych, like we did in example 3. Whatever your preference is. I just wanted to show you both. can we flip when we're ready? And can you put a star beside example 4 and example 5? Both of them are what I'm going to call higher end questions. They're not your classics. 1, 2, and 3 are classics. Okay. There's a 40% chance that it's going to rain on Friday. If it rains on any given day, it's 10% less likely to rain on the next day. If it doesn't rain, it's 20% more likely to rain the next day. What is the probability that it'll rain at least once on the weekend? Now, they're considering Friday, Saturday, and Sunday to be weekend days, okay? So I don't want to, we're not going to argue about that. They're considering Friday, Saturday, and Sunday. So what makes this a more challenging question are these little words right there. As soon as you see them in the question, you know that it's a stochastic, you know that it's more challenging. So let's leave the numbers aside for now, and let's do our Saturday, Sunday. Friday, Saturday, Sunday. Rain or not, 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 rain or not. Same old tree diagram. So rain, rain, rain for the whole weekend. Raining on Friday and Saturday, but not on Sunday. Raining on Friday, not Saturday, but Sunday. Raining Friday, not Saturday or Sunday. Doesn't rain on Friday, but rains on Saturday and Sunday. Doesn't on Friday, but rains on Saturday, nothing on Sunday. No rain Friday or Saturday, but rains on Sunday. Oh my God, no rain the whole weekend. Okay, now we got to go back and muck around with the numbers. So let's go back to the question, and it says there's a 40% chance of rain on Saturday, meaning that there's a 60% that it doesn't. That part's easy. Okay, now, if it rains on any given day, it's 10% less likely to rain. So 10% less likely from the probability of raining makes it a 30-70. So hold on. If it rains on any given day, it's 10% less likely to rain on the next day. Let's keep that thought going. If it rains on any day, it's 10% less likely to rain on the next day. Okay, not so bad. Here's where I need you to stick with me. If it doesn't rain, if it doesn't rain, if it doesn't rain, it's 20% more likely to rain from the probability of raining. So if it doesn't rain, it's 20% more likely to rain from the probability of raining. If it doesn't rain, it's 20% more likely to rain from the previous probability. If it doesn't rain, it's 20% more likely to rain from the previous probability. So we're always going from the previous probability, 20% more likely, 20% more likely, 20% more likely. Oh, I think we forgot one branch. If it rains, it's 10% less likely. So you can see very, very clearly why this one's harder. Okay? Now, let's actually see what the question's asked. What is the probability that it rains at least once? Rains at least once means 1 rain, 2 rains, or 3 rains. What's the best way of doing this? I hope you're thinking about it. I hope you're thinking about it. This one is a no-brainer of reverse psych. 1 minus the probability of 0 rains. 0 rains would be this option or this branch right here. That's my 0 rain. No rain, no rain, no rain. So 1 minus 0.6 times 0.4 times 0.2, 0.048, 95% chance that it's going to rain at least once. Now, could you have done it direct? Yes, you would have had to add this. You would have had to run 7 iterations of the stochastic. And again, you know, your chances of making a silly, you've already seen me make a silly today, are pretty huge. Love that question. Love it. Let's take a look at the next one. Mr. Cirilla goes to Empty Bellies, and he orders a Shirley Temple. After the first one, he's 90% likely to order another one. For each additional Shirley Temple he drinks, he's 10% less likely to order another one. What is the probability that he stops after the 4th one? So right away, when I saw this question ages ago, and I read the word stops after 4, I thought, oh my God, that's going to be a massive tree diagram. We're used to doing tree diagrams with 3 coins, Friday, Saturday, Sunday, 3 games, 3 questions. So I thought, geez, I better take a few little seconds here to maybe draw this out. So there's Shirley Temple number 1, Shirley Temple number 2, Shirley Temple number 3, Shirley Temple number 4. Okay, let me think about this. I'm going to call them Shirley or not. 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 This is getting way too big. It's kind of getting a bit confusing. I'll think about it. Let's kind of think about it here. And let's put some numbers. I'm just going to leave this for a second. I may have to draw it in. I don't know. Let's take a look at some numbers. It says after he has his first Shirley, after he's consumed his first Shirley, he's 90% likely to order another one. Okay, I feel good about that. For each additional Shirley, he's 10% less likely. So if he's 90 on the first, 10% less likely, 10% less likely. Okay. I'm using all the numbers. What is the probability that he stops after consuming the 4th Shirley? So here's Shirley number 1. Here's Shirley number 2. Here's Shirley number 3. Here's Shirley number 4. This would be the next Shirley, but he's stopping. So hold on, 10% less likely. So that would make that a 60 and a 40. So hold on, bear with me. He has the first Shirley. He drinks the second Shirley. He drinks the third Shirley. He drinks the 4th Shirley. but then he stops. Cool. 0.9, 0.8, 0.7 times 0.4. So drinks the first Shirley, 90% that he's going to have the second, 80% that he's going to have the third, 70% that he's going to have the fourth, and then 40% that he stops. Very cool question. 20%, 20.16%, that's what he does when he goes to empty bellies. Really cool lesson. Your homework is a handout on stochastic processes. The final solutions are at the bottom of the handout, and I included a beautiful PDF of full solutions. There is a couple of them that you'll definitely have to look at my PDF. Okay? Take care. Bye-bye.